I think we can start directly with my screen. So if people followed 2 weeks ago or later on YouTube, because we put the recording on YouTube, we have seen basic things on indexes, mainly on one table, countries. It's a table with countries and names and ID codes and small data, but the idea is to look at the execution plan and some execution statistics.
Yep.
And do some search like this one, looking for a country by a country ID, and country ID is the primary key. So that's easy. We store tables in the primary key, and finding data from with a predicate on the primary key is fast. So this is basically what we will see in all cases. The execution plan tells me that it's an index scan and the predicate on the is on the primary key using the index.
Zooming up even one more level, Frank, I think we talked about how the primary table and the index table are just all their own distributed tables, right? Spread across nodes and sharded and replicated and all of that, and all of this is spread, right?
Yeah, exactly. Okay. This one is hashed, and we will see the shape of indexes by doing some selects. But the idea is that here the query is fast, and we read only from one tablet at a specific place and with just a few values. I will run another query now, so resetting the statistics and doing an execution plan. Sorry, I just missed my point. There, this was country ID, and now I want to show the same as we did before with the country code, which has no index there. I removed the indexes that I've created the last time, just to show that if it's not the index, we have another code, sequential scan, reading all the tablets, reading at many places, and this is where we want to optimize. So last time we created an index on it, and now I want to show how it works. Basically, the index is a sorted structure. So here, I've run just a select that is there, ordered by country ID and with the hash code. So this is exactly how it is stored internally in this order with the hash code. And
the hash code is the sort order, correct? The hash code is effectively the bucket it goes into.
So that's the way we shard on a hash. We put a hash code in front of it and then process it as the other columns. And then a sequential scan reads everything like this, and this is why it's long. Basically, what does a sequential scan when I'm reading for? So this is, for example, what we have there. I just want to go to the end to show that if I look for the country code CHE, it first gets the hash code, and that's something that we can find. For example, I will go there and search on my screen to this value. It goes directly to this value, then to the code, and then as the line. So by primary key, everything is fast. Without the primary key, the goal of the index will be to map that to a primary key and then go to the table with primary key.
Yep, and we also, I think, talked about covering the columns, right? Including the columns, so you don't have to do that extra jump.
So the basic index will be on country code will be sorted like that. So I have the codes and then the hash code and the primary key to go later to the table. Like if I have CH, I have enough information now to go fast to the table. But if I add more information in the index, I will have something sorted also on country code, with information to go to the table, but with more information. And for example, here, I have a name and official name for those countries. And now we will see how we can create indexes for queries on those names. So going to the end of that. So I want to query something on the name. And then I want an index structure sorted on the name, like I did here with order by official name. And now let's say I want to find all the countries starting with a S. in a structure like that, it's easy. They are all at the same place.
Yep.
So it's a range. Except that this colon is the official name, and I see that some countries have no official name, just the normal name. And there I may have some ones starting with S, for example, this one.
Yeah.
And this is where in real life.
So let me get this right. So let me get this
Yep.
right. What we're trying to do here is there are two columns. One is the colloquial name or the commonly used name, and the other is the official name. And the question, the query that we want to serve up is what countries start with an S, whether it be on the common name or on the official name, either, right?
Yeah.
And I think to make things more complicated, there are a bunch of countries that don't have an official name. They only have a common name. So the official name is empty. And if we really did an index, all of those would point to a null value, and the null value would be the biggest value, and it'd be really slow, right, to do any operation. And
in real life, we have things complex like that, like this query, looking for countries starting with S. I use a S in a like, but in order to search first on official name, if it exists, and if not on name, we have a function for that in SQL, coalish. It returns the official name if there is an official name. If not, it returns the name. And in addition to that, usually when people look for something starting with a letter, they don't care about uppercase or lowercase.
That's right.
And this is why the query that the user will do or the application will do, well, will finally have a function. So this is what we want to index. And that's the main point here. People think that you index table columns, but you really index what you want to query and to search. And here, this is what we want to index. And of course, we can do that. And now we will create our first index. And it's quite simple. Instead of mentioning a colon here in the create index, I mentioned the function. And an expression, the best name is expression because it can be more than a function. Here we have two functions. And we need additional parentheses there so that the syntax parser knows that it is a function. In this case, because it's a function, I don't think we need it. But for example, if we have expression with plus, minus, then we need those additional index parentheses. So here I create an index, which will start with this value, will be ordered, not hashed here because I want a range. So ordered by this value, which then will be able for some value to go to the table with the primary key. But let's check the execution plan for that. So that's the plan and the statistics, and we will look at that. So index scan on this index that I have created, I've put a large name, but usually it's better to put some abbreviation. The index condition comes from my query. The like S is like a range between S and T. And we see the coalish function, and we see the upper function. So this is solved by the index. The 13 rows are found directly in the index. And here I can see, so this is the tablet for this index that stores one tablet of this index. And we go directly there and read a few columns from there. But we still have to go to the table because my query is also reading official name, country ID. And that's important. We have seen that with covering index 2 weeks ago. But here it can be misleading because if I look at the index creation there,
it does seem to have it, yes.
You may think that you have the official name and the name within the index, but you just have the result of the function. And with the result of the function, you cannot know if it comes from the official name or the name. So even if the result of the function on this column is in the index, if the columns are not in the index, Yugabyte has to go to the table. And this is where we will create a covering index like we have seen like that. And you see that I've added country ID. You remember this question we had? As the primary key is in the index to be able to go to the table. If we query the primary key, why do we still have to go to the table? It's nearly the same as with those ones that are function. We have the primary key, but we store it in a different way for the moment. But it's easy to work around. If I want to query the primary key and with an index-only scan, I can just add it there, and then we will see the execution plan. For this one, I expect an index-only scan. And reading only the index, the values from there, index-only scan.
Yeah.
And for all those queries, yeah, sorry.
To dwell on this, right? Like if we go up to the previous execution, because the index was not a covered index, because we had to go to the index table to find out the set of rows and then go to the actual set of rows. If you go back to the snap table, execute the statistics above. So what that means is we are now incurring about 4 RPCs, right? Like we go look at the index table and the index table says, hey, this is what I really need. And whatever you really need is in the other 3 tablets, which could be on 3 other nodes. So that's 4 RPCs from the query transaction coordinator, right? Whereas in the second example, that's just a single RPC, which is satisfied, the one that you just did. This is a single RPC to the index table and it's just satisfied. So the latency would be that much quicker, but we are trading off latency here for data storage, right? Because the index is now including the covered columns, right? So, and I guess this is an interesting point because in the cloud, storage is often cheaper than compute. So covered indexes are actually more interesting, but I mean, the trade-off, of course, is you have to write more data, but your reads will be much quicker. Right?
Yeah, for the storage, I really don't care. It's more when you know that you will have updates. If you have frequent updates on those columns, then if you include them in the index, they have to be updated. But here, in this case, anyway, if we have updates on them, the index must be updated because the function must be calculated and update the index. So and same for the primary key that we have there. It's also in the index. Usually we don't update the primary key. Actually, but in this case, I don't think there is a lot of overhead on DML. So it's only storage, and yeah, that's
I think
not
you made the other good point, which is just worth calling out, right? So unlike Postgres, one difference is that YugabyteDB will only update the indexes for like that contain the columns that have changed, correct? So if I have a 20 column table and I have 3 indexes on it, say on columns 1, 2, 3, and I change columns 4, 5, 6, 7, all of the other columns, none of these other indexes would get updated because they don't really contain the column unless either the index or an included column is present, and we'll only then go and update that, right?
Yeah, we really store column value where in Postgres the whole row is written except if you reserve some space in the block, but yeah, people rarely do that. And also in Yugabyte, when you see index-only scan, you are sure that it's an index-only scan. Postgres has still to look at the table for the visibility. We store the visibility with the index. So yeah, more and more reasons because of the storage of Yugabyte and because we are in the cloud with RPC, there are more reasons to shape the indexes for the queries. Maybe not all queries, but where performance is critical, where you want single-digit latency, then you should expect this kind of plan and this kind of statistics, and then you build the indexes for that. Yeah,
makes sense.
So that's really the idea. You have tables, you have many queries, and the goal is to have a set of indexes that will be a subset of your data, but a subset of your queries, so that your critical queries will find a fast path into the indexes.
So I have a question. It's triggered, like, I think I don't know how much more you have. I'm just maybe dragging you off, but I have a question. So how does row level security work with something like a covered index?
Yeah, row level security just is similar to adding a where clause, and then yeah, that's a good point. You need to take that into account when indexing. if you know that your row-level security will add a where clause on all your queries, then you should find this this colon in the index. Yeah.
Got it. Got it.
So it can be, if it's multi-tenancy, there are good chances that you find this colon in the primary key. But yeah, in any case, always good to look at the execution plan, because and the execution plan with the right user. If you use a row-level security with different users, if you use it with the super user, and then you don't have the same where clause, so looking at the execution plan. And also something that is really interesting, so not new for SQL databases, but people don't have that in NoSQL databases. I didn't add any int here. I didn't query the index. I just used my query, and the query planner is aware of the existing index and is there to find the best one.
The best index, right, to use, or the best set of indexes to use. Yeah.
Yeah, the best index. Yeah, yeah.
Makes sense.
So in complex query, there may be cases, especially if we don't have statistics, there may be cases where it's difficult for the query planner to find the best index, but also you should have only the required set of indexes. For example, here I just created more indexes, but I should remove the old one in this case. For example, if I describe countries, yeah, this index, which is the same as this one, except that it doesn't include those colons, is probably not useful. It's just a bit smaller, but there is no reason to maintain those two indexes. So this one should be removed if we have this one. Yeah.
Yeah. Yeah, makes sense.
And now, because the goal of indexing is shaping the data for the query, so shaping with the order of rows, shaping with selecting the columns that we need, we can also select the rows that we need. We don't have to index all rows. And for this one, so for partial indexes, here is an example. So the same query, except that in my case, the users who search on the first letter for the country search it only for Europe. I don't know why. Maybe there are too many countries in Europe, and in others, they don't do this search. So let's say that this query, so this index is needed only for queries which add region ID equal Europe. And then I can create an index, same as before, adding a where clause. So this one is simple. For the other one, it's different than what we see in the select. In the select, we see columns. Here, we add them with include. In the select, we see an order. Here, we add them in the index definition. Here, it's simple. It's just the where clause. So this creates an index that index these columns in this order, but only for some rows. And now, if I run my query again, I run directly the explain plan and the statistics. So statistics are not very different because my index is smaller, but I still go directly to one place. But what's interesting is that region ID equals EU. We do not see it anywhere. With usual indexes or sequential scan, we find the predicate either in the index condition or in a filter. But here, it's not there because the planner, the query planner knows that when it reads from this index, all rows are about this region. So it's something that is filtered not by doing less work, it's really filtered by just not doing the work. There is no need to do this filter.
Yeah.
And that's really interesting in some cases.
I think this can actually be used for a number of other queries, right? Like show me all the countries that don't have an official name, or you want to run that like query with only on the official names, but you don't want to, you want to filter out all the null official names, right? There could be a bunch of them that don't have it.
And sometimes you have big tables where you have a flag like orders to process flagged with a yes. We have booleans also, and the small order to process, and when they are processed, the flag goes to no. And you really want an index only to know which one to process, because the one that have been processed, the index selectivity is not good. There are a lot of them. So this is a case, for example, where you can build an index just for the small set that you will query.
Got it. Like implementing a queue almost, right? Like implementing a queue in SQL, kind of. Like
yeah. And the beauty of it is that the index is maintained automatically. You don't have to maintain it. You don't even have to mention it in any query. It is maintained automatically and in sync and consistent.
Yeah, makes total sense.
Looking if there are questions, not a lot of questions today. I have another example. So first, the definition of the index. If I describe the index, we can see it. The definition is really similar to a table, because an index is like a table. And we just have a mention if it's the key or not. So the result of the function is the key, and the other columns in the includes are just there, not being the key. And the predicate is there. And we can also, if we forgot the DDL that we use to create the index, we have also a Postgres function to get it. So we see it.
That is pretty cool. I didn't know that existed. Okay, that's pretty cool.
Yeah, and you also see all the things that I didn't mention. For example, we know explicitly that the data type is text here. We know explicitly that it's LSM tree and all that. And I have another example with functions. In my country table, I have also the population and the surface area. Okay. So those are interesting things. And let's say that users want to know the highest density countries. So the information we have in the table is population and area. But what people want is divide them. This query shows me the query with more than 1,000 people per square meters. And that's a lot. Huh? So Bangladesh is a big country with high density, and we have small countries like, we have a few like that in Europe, like Monaco or Vatican, just because they are small, so there are a lot of people there. So for this kind of query, we see that we filter on an expression. It's not a function, but it's an expression. So it can be interesting to use a function-based index, an expression-based index on that. And also, we will query only for high density. So maybe there is no need to have in this index entries for other countries. And here,
but before that, like maybe can we look at the explain plan before we, or too late? Never mind.
No, I can drop it. I can.
Okay.
Yeah, I didn't show it, but I expect nothing else than a sequential plan here.
Yeah, full scan, right? Yeah.
But I will. Just taking the explain plan from there, because I put cost off just so that it's not too wide when we show it on the screen. And this was the query. And my function execute snap table. Yeah. So we have the sequential scan, which output all this information that I need. The filter occurs later, and then the rows removed by filter. So this means that we have read many rows from all the tablets.
Yeah.
And the Postgres part has removed then according to this filter, because the information was not stored. And also a sort, because I have an order by. The idea is also to see first the highest density ones. So that's a sequential scan. Here I have a small table, but you can imagine on a big table the cost of it. And I create then the index. And the interesting thing here, I know that I will query for density higher than 1,000 people. But to make it more complex for the optimizer, I do not create my index only for those one. I take a larger one, every country with more than 500 people. So I have more rows than what I need for this query, but maybe I have other people querying for other things. And now the goal is to see if the query planner can figure out that this one is included in this one.
Yeah. Yeah, because it's not an exact match this time.
And of course, I tested it before and it does, but I have no doubt because this is Postgres and Postgres exists for years and years and years, and there's a community and all those things are put by the community. So here I see the index condition that I used, but it used my index, where is it? Countries density. So my index that I've created for all countries with more than 500 people per square meter can be used to filter on that also. And because the index is ordered on the population, it's directly a range. So the partial index is a range of some rows of my tables. And within this index, I can read a smaller range of it.
Awesome. Fantastic. Fantastic. Yeah, I think that is pretty cool that the partial index and the actual query don't match, right? Like it's a subset, but the query planner computer, it really figures it out what index to use.
And these partial indexes, it's not something that exists in all databases. For example, in Oracle, there is no partial indexes. You need to partition the table to do something like it. And that's more complex. Here, we still have partitioning, for example, for the region. Maybe I want to partition it, but for the top density of population, I don't want to partition on that. I just want an index for fast access for the queries on that. And only if it makes sense. If I have people also querying for the low density countries, for example, we can do that if I explain. So I don't know if there are a lot with less than 10 people, for example. Yeah, if I have queries like that, my index cannot be used for that.
Yeah, because I will have those rows. Yeah, yeah.
So it's important to know the access pattern, but also this can change. You don't need to know everything in advance for the next years, because creating an index is an online operation. You just have to manage it, not to create too many indexes, but of course you can add them later if you realize that you need something else.
Fantastic.
So it can also make sense in this case to create an index on the very high density and very low density, because all the rows in the middle, probably people do not query on that.
Yeah, and then that's going to be pretty efficient because a row is either high density or low density. So when you do an update, you don't incur a double index update cost, right? It only does this or that.
Yeah. So. Yeah. Only the update on those countries will have to update the index. And that's interesting because the population, that's something that you may index update frequently. But if you have only 10 rows to update, it's not the same problem as all the rows. Yeah.
Makes sense. Makes sense. Awesome. We have a quiet crowd today. Any other questions, folks? Anything you would like to know? Last time there were a ton of questions. So
yeah, there are days like that. Anyway, questions on the Slack channel. If I put the next slide. So we have a Slack channel for the community. We have everything on GitHub, not only the code, but the architecture, the roadmap, everything. It's easy to find us on social network as well. And the recording goes to YouTube in a very short time. If people go to YouTube immediately in a few minutes, maybe the quality is not good because it's uploaded first, but the high quality is available after a few hours or something like that.
Fantastic. Awesome. All right. I think that brings us to time. So thank you everybody for joining us. And
And next time, I think it is about PG int plan. So again, a lot of plant. I think it's one that presents that.
Right.
And so again, execution plan and more control on them.
Awesome. Fantastic. Thank you, everybody. As Frank said, feel free to join us on our Slack channel and see you guys next week. Same place, same time.
Bye.